Good morning, ladies and gentlemen. The title of my presentation today is Rocket and Wire Triggered Lightning. This type of lightning is also referred to as triggered lightning or just rocket triggered lightning, or RTL. So the meaning is the same, just different names. After a brief introduction, I'm going to introduce the rocket and wire lightning triggering technique and give an overview of major lightning triggering programs. And after that, I'll give just a few examples of using triggered lightning or triggered lightning data for a variety of purposes. Just a few examples because we must finish by 10:50. And those examples will include testing vulnerability of underground power cables to lightning, evaluation of the performance characteristics of lightning locating systems, and estimation of lightning input energy. The first question to answer is, what is rocket and wire triggered lightning? It can be defined as a full-scale lightning discharge between a natural thundercloud and a designated point on ground that is artificially initiated using the so-called rocket and wire technique. So important words here are full scale. Full scale means currents up to tens of kiloamps and potentials, electric potentials of the order of 10 megavolts. So this is not possible in laboratory. The other key word here is natural. So the energy tapped by rocket triggered lightning is naturally accumulated in a thundercloud, which otherwise would produce natural lightning. The rocket and wire technique involves the launching of a small rocket, usually 1 meter or less in length, extending a thin wire, could be grounded or ungrounded, toward the charge cloud overhead. And in most respects, the triggered lightning is a controllable analog of natural lightning. First triggering was done in the United States in the 1960s over water. And the first journal paper on rocket triggered lightning was published more than 50 years ago in 1967 by Newman and collaborators. And the middle panel here shows a still photograph of rocket triggered lightning taken at a distance of 2 kilometers. The left panel is a sketch of the same lightning. And here you can see the research vessel from which the rocket was launched. And this portion of the channel, about 100 meters long, is the segment of the channel that was determined by the triggering wire. And it's, as you can see, it's a very small fraction of the overall channel length, which is of the order of kilometers. And the right panel is just a close-up view of rocket triggered lightning, and at distances the order of tens of meters, you can see lightning channel swept by wind blowing from right to left in this case. The second question to answer is, what can we learn from rocket and wire triggered lightning experiments? Is it useful? Is it good for anything? And the answer is yes, of course. Results of triggered lightning experiments can serve to understand better the physics of the natural lightning discharge. Also, to improve lightning protection schemes via direct testing of those schemes with full-scale lightning. They can be also used to obtain ground truth data needed to evaluate the performance characteristics of lightning locating systems, and also can be used for testing the validity of lightning models. Triggering technique. What you see here is the spatial distribution of electric field produced by overhead thundercloud, and two typical values of electric fields at ground level and at a height of about 200 meters are given, 5 kV per meter, 50 kV per meter, and equipotential surfaces. So solid lines here and broken lines are equipotential surfaces. And in the absence of rocket and the trailing grounded wire, the equipotential surfaces are just horizontal planes. And the potentials and megavolts are given on the right here. When the rocket trailing grounded wire is launched, then the ground potential is transferred to a height, in this case, about 150 meters. And as a result, the equipotential surfaces are geometrically concentrated near the tip of the rocket, which means the electric field is enhanced at the rocket tip. And when the electric field exceeds the critical breakdown value, there will be the so-called upward leader initiated from the tip of the rocket. It's a hot plasma channel that will propagate toward the cloud. And this is different from the case of natural downward lightning, which starts in the cloud. Rocket-triggered lightning starts at the upper end of the triggering wire, grounded wire. In some respects, rocket-triggered lightning is similar to lightning initiated by tall objects. For tall objects, upward lightning also starts from the object tip and goes into the cloud. This slide shows the sequence of events in classical. When I say classical, this means the triggering wire is grounded. It can be ungrounded, floating. Negative rocket-triggered lightning. For this polarity of lightning, and polarity here is determined by the polarity of charge effectively transported to ground. The direction of electric field vector is upward, and going from left to right, here you can see the ascending rocket. The speed is of the order of 200 meters per second. And when the rocket is at a height of roughly 300 meters, this is typical for Florida. In New Mexico, it could be 100 meters. The electric field enhancement at the rocket tip is high enough to launch this upward positive, in this case, leader. So the current associated with this upward leader will burn the wire, usually made of copper, or sometimes in steel, and the wire literally explodes and creates a gap between the rocket and the rocket launcher. So the gap of the order of a few hundred meters. And this gap is rapidly replaced by a plasma channel, as shown here. Actually, there will be a descending negative leader that makes this happen. And the upward positive leader will continue to propagate into the cloud and apparently heavily branched inside the cloud. And here below the cloud base, we see there's a quasi-stationary arc, current of the order of 100 amperes, and that arc is burning for times of the order of hundreds of milliseconds. So this is usually called the initial continuous current. This is upward positive leader. And the two together are usually referred to as initial stage in rocket-triggered lightning. Well, when the initial continuous current gradually diminishes and luminosity of the channel fades off, then this broken line indicates the channel is not luminous, and the current that can be measured at the launching facility is essentially zero. And in 25% of cases, rocket-triggered lightning ends. So it consists in 1/4 of the cases of the initial stage only. But in 75% of cases, after this no current interval, typically some tens of milliseconds, there are leader return stroke sequences. And the leader propagates downward, the typical speed 10 to the 7th meters per second. It's a dot leader because it follows the remnants of the previously created channel. It deposits negative charges onto the channel, and when the connection to the launching facility is made, the return stroke propagates upward, typical speed 1/3 of the speed of light. It neutralizes effectively all the negative leader charges. So leader return stroke sequences, they're just charging, discharging processes. Only one sequence, leader return stroke sequence, is shown here, but could be 5, could be 10, could be 15 or more. This is a still photograph of rocket-triggered lightning, but it is actually time resolved by the action of wind blowing from left to right. This sharp edge here indicates the wire explosion and the initial stage current. So this portion of the image is initial stage of rocket-triggered lightning. And then there are 3 distinct channels separated by dark gaps. Those are leader return stroke sequences. So leader and return stroke are not resolved here, of course, but each of the three channels is a leader return stroke sequence. This is just to show the difference between rocket-triggered lightning and natural lightning. You can see sketches of current records at the channel base, or at the rocket, well, at the channel base, yes. And for natural lightning, well, we have stepped leader, which is not producing any current at ground, followed by the first return stroke, and it is shown here. Then there is a interstroke interval, and there could be one or more, typically more than one, subsequent strokes. Any stroke other than the first we call subsequent stroke. So there are three shown here just as an example, and beside the impulsive components there could be steady currents that we call continuing currents, and here the second subsequent stroke or the third stroke in the flash was accompanied by continuing current. In the case of rocket-triggered lightning, there is no first stroke, there is no stepped leader propagating from the cloud to the ground. What we have instead is the initial stage. It lasts for hundreds of milliseconds typically, and the currents are low, of the order of 100 amps, as opposed to 10 to 100 kiloamps for first stroke, but this is impulsive component only. And 5 coulombs, this is charge transfer, typical for first strokes. And for the initial stage, typical charge transfer is 30 coulombs. Subsequent strokes, if it's impulsive component only, whether it's natural lightning or triggered lightning, is 1 coulomb. With continuing current, 10 coulombs is typical value. Major triggered lightning programs. In this table, I list information about the location of the experimental site, height above sea level, years of operation. The wire material is either copper or steel. Location of wire spool could be a rocket or ground, and some selected references. As I said earlier, the first rocket-triggered lightning experiments were done over water. The French researchers perfected the triggering technique over land, and they also participated in triggered lightning campaigns in Florida and New Mexico and in Brazil. So the experimental sites, France, I already mentioned, then Kahokogata site in Japan. This is where the famous winter lightning occurs, Hokuriku Coast. Langmuir Lab, New Mexico, the Kennedy Space Center, Okoshoshiku site in Japan, 7 different sites in China. Here, relatively short but very productive triggered lightning program at Fort McClellan, Alabama. Camp Landing, Florida, you heard about this in the Franklin lecture, and Cachoeira Paulista, Brazil. The blue color means the triggered lightning program is either active or capability maintained. All others are terminated at this time. The first successful rocket and wire triggered lightning in China was produced in 1977 by the Chinese Academy of Sciences. Since then, more than 300 flashes were triggered at 7 different sites, and they're all indicated here by magenta stars. So as you can see, all over China. Presently, 2 triggering sites are active. One in Binzhou, operated by the Chinese Academy of Sciences, and the other one in Zhonghua, operated by the Chinese Meteorological Administration. Many different experiments were conducted in Japan. This is just one example. In this case, the triggered lightning current was injected into the car with a live rabbit inside. And I can say up front that the rabbit was not harmed, which was a direct proof of the Faraday cage effect. And you can see here that tires were flashed over here and here, and you can also see ground surface arcing. And in Japan, the triggered lightning experiments were conducted in winter, so it's snow here. This photograph is from Fort McClellan experiments. Here you can see the smoke from the rocket. This is wire residue. And the main lightning channel is not seen because the main channel attached to 11-meter long strike rod here. What you can see instead are ground surface arcs. So they develop in different directions, and one of them extended over 10 meters or so. So these ground surface arcs certainly represent a threat for various assets and for human beings and animals. Any presentation should contain at least one animation or video clip. This is mine. Let's see if it works. Rocket goes up, and here is rocket triggered lightning. The rocket launcher was mounted on a utility bucket truck, and the current was injected into the test power line. This is what this was about. One more time. And the line, of course, was instrumented. Currents and voltages were measured everywhere, and very valuable information was gathered from that experiment. So far, I was talking about classical triggered lightning, triggering wire grounded, but it is possible to trigger lightning with floating wire, not connected to ground, and this is one example from Brazil. This straight section of the channel indicates where the floating wire was. It exploded, of course, and was replaced by a plasma channel. This tortuous channel above the straight section was created by upward positive leader, and the downward negative leader developed from the bottom of the wire. So this is so-called altitude triggered lightning as opposed to classical. And I move to the three examples of using triggered lightning or triggered lightning data for various purposes. We'll start with testing vulnerability of underground power cables to lightning. And tested in this experiment were three 15 kilovolt single-phase coaxial cables buried 1 meter deep and 5 meters apart in sandy soil at Camp Landing, Florida. And the cables differed only in the level of their insulation from the surrounding soil. Other than that, the insulation between the center conductor and the outer shield was the same. Polyethylene insulation, 15 kV. It's just the level of insulation relative to the surrounding soil. This is a kind of a schematic. The three cables are shown here, buried 1 meter deep. The one in the middle, labeled C, had a bare neutral in direct contact with the soil. Cable B was the same as cable C, but had insulating jacket covering the concentric neutral. And finally, cable A was the same as B, but placed inside a PVC pipe. So this is where the cables were located. The rocket launcher was placed on ground surface on wooden rails and could be moved perpendicular to the cable to place it at different position with respect to those cables. This was the very first experiment at Camp Landing, conducted in 1993. And in 1994, next year, the cables were excavated to see what happened to them. So I'm going to show photographs of the cables, and I'll start with cable C, which had no insulation with respect to the surrounding earth, then cable B, which had insulating jacket, and finally A, with the best insulation from the surrounding soil. This is a bare neutral. It's a stranded or multi-strand conductor, and several strands are melted through, and the polyethylene insulation between this neutral and the center conductor is damaged, severely damaged. So this cable definitely experienced lightning failure. The next one cable B, it had insulating jacket, polyethylene insulation. And it was also severely damaged, and you can see here fulgurite, which is a glassy tube made by lightning current when it flows through sandy soil. So this cable didn't survive either. And finally, our best hope, the same as B, this cable A, but inside PVC pipe. You can see a hole melted through the PVC pipe wall, and it's deformed, and the cable inside was damaged similarly to what you see here. This is a section of fulgurite. So, 3 levels of insulation: the insulating jacket, the air inside the PVC pipe itself, and 1 meter of soil did make this cable invisible to lightning. And as a result of those experiments, it was determined that lightning strikes to ground or to a grounded object, tree for example, within 10 meters of underground cable are likely to terminate on the cable and result in damage to that cable. Evaluation of performance characteristics of lightning locating systems. I'm going to show results of such evaluation using as ground truth rocket triggered lightning data only for the US National Lightning Detection Network, NLDN. But similar evaluations have been also performed for 3 other networks: ENTLN, Earth Networks, Total Lightning Network, Woolen, and GLD 360. Lightning locating system performance characteristics. They're all defined here. First one is the detection efficiency, and it's the ratio. In the denominator, we have the total number of events, and for rocket-triggered lightning, we do know that because we manufacture those events. And the numerator is the number of events detected by a lightning locating system, usually expressed in percent. And events here could be strokes or could be flashes. And for flashes, the detection efficiency is necessarily higher than for strokes, because in order for a flash to be detected, only 1 stroke needs to be detected. Percentage of misclassified events. All the strokes in rocket-triggered lightning flashes used in this evaluation were negative CGs, of course. And therefore, any of them reported as either positive events, positive CGs, or intracloud pulses, ICs, were misclassified. So we just found the percentage of such events, and this is the second performance characteristics on this list. Location error, this is straightforward. It is just simply the distance between the location of rocket launcher, and that location is known precisely, and between the rocket launcher and location reported by lightning locating system. And finally, current estimation error. This is the equation. LLS is just lightning locating system. I'll be talking about NLDN, but it could be GLD 360, Woolen, or any other network. And CB stands for cam blending, because cam blending data were used in this evaluation. So it's just the difference between the ground truth value, the value reported by the system, divided by the ground truth value, expressed in percent. And as a reminder, this disclaimer at the bottom, the results of this evaluation, strictly speaking, apply only to subsequent strokes, because there are no first stroke in rocket-triggered lightning. However, detection efficiency, location accuracy for natural lightning, when there are first strokes, are expected to be higher than for rocket-triggered lightning, because first strokes are usually more intense and they're easier to detect, and location errors are usually smaller. The configuration of the NLDN in the Florida region is shown here. 17 NLDN sensors are indicated by gray circles. There are 17 of them, including 2 in the Bahamas. And location of the cam blending lightning triggering facility is indicated by a black circle right here. Results. From 2001 through 2015, the evaluation of the performance characteristics of NLDN was performed 4 times. And during that time period, spanning 15 years, there were 2 major upgrades of the NLDN. The first one was completed in 2004, and the second one in 2013. And different time periods you can see here. I'm going to talk about the second column and the last column. For the second column, the time period is before the first upgrade, and the last one is after the second upgrade. So, if you look at the flash detection efficiency row, it was 84%, and now it is 100%. Stroke detection efficiency, 60%, 86%. Percentage of misclassified strokes was not determined in the earlier study, 5% presently. Median location error, 600 meters, now 162 meters. And finally, the median absolute current estimation error, 20% and 15%. To me, it's surprisingly low. I'm talking about the current estimation error, because currents are not directly measured. They're estimated using a model or some empirical formula from measured fields. And 20 to 15% is pretty good. And finally, I'm going to talk the experiment in which lightning input energy was estimated. And this was one of the results of collaboration between the University of Florida and the Central Research Institute, the word institute is missing, Institute of Electric Power Industry, CRIPI, Tokyo, Japan. And that joint experiment was aimed at measuring electric fields in the immediate vicinity of rocket-triggered lightning channel. Immediate vicinity here means 10 centimeters, and Pockels sensors were used for those measurements. And besides the input energy, channel resistance, per unit length, and channel radius at the time of power peak were estimated. What you see here is a sketch of the lightning channel. It's just a cylinder. And for rocket-triggered lightning, currents are routinely measured. So current is a function of time. It is always available, or almost always available, for rocket-triggered lightning. And if we knew the longitudinal electric field inside the channel, then the product of the current and the longitudinal electric field, as seen here in the yellow box, would give us power per unit length. And this is the lightning input power per unit length. We can, of course, integrate this power over time, and it's going to be the input energy per unit length. Well, the problem here is that measuring electric field inside the lightning channel is kind of difficult, but fortunately, if you measure it outside the channel but close enough, you don't make a significant error. In fact, the tangential component of electric field is continuous across any boundary. So if we measured on the surface of the channel, it would be the same as field inside the channel. So we measured field at 10 centimeters from the lightning channel, used measured current, found power per unit length, energy per unit length. It's also possible to estimate the resistance per unit length just as a ratio of E and I. And if you can make a reasonable assumption about electric conductivity, sigma, you can estimate the radius. And lightning input energy is an important parameter needed in a number of areas, including the estimation of NOx produced by lightning, evaluation of lightning shock wave effects, and testing of thunder generation theories. This is a configuration of the experiment. The rocket launcher was below ground surface. There were different configurations used. In the Franklin lecture, you saw the tower launcher and the portable launcher. I showed you the bucket truck launcher, and this is underground launcher. Strike rod, 2 meters tall, and the Pockels sensor was installed in a plastic holder right here, and these are fiber optic links. The focal sensor is a crystal that changes the index of refraction in the presence of external electric field. Fields were measured, current is available, this is field, this is current, this is power, unit length, and this is energy. And to conclude, results of triggered lightning experiments have provided considerable insight into nature lightning processes that would not be possible from studies of nature lightning due to its random occurrence in space and time. Triggered lightning experiments have contributed significantly to testing the validity of various lightning models. Didn't have time to talk about that, but believe me, very important results. And providing ground truth data for testing the performance characteristics of lightning locating systems. Finally, triggered lightning is a very useful tool for studying the interaction of lightning with various objects and systems and testing lightning protection schemes. Further reading on this slide, and I have to finish. Thank you for your attention.